So this video lesson is for Chapter 1, Day 1, the very first day, and we're going to look at 2 of 3 different ways to add vectors together, something that we'll be doing quite a bit through Physics 12. So this whole chapter I'm actually going to call like Physics 11 all over again, but with a real emphasis on vectors, especially two-dimensional vectors. And here we go. I'm going to dive right in. Let's kind of figure out where vectors fit into the picture here. For Physics 12, we're going to say that there are 2 different types of quantities out there that you can be measuring. One of them are scalars and the other are vectors. So scalars, what's important about them? They don't have any direction. They only have size. The fancy word, if you want to get all fancy and use big words, you can say they have magnitude. Okay? I like to joke around and say they have bigness. But they don't have any direction to them at all. So here are some examples of some scalars that we would have used in Physics 11. All of these things, time, mass, speed, distance, they all have size. You can talk about how big they are, but they don't have any direction like north, south, east, or west. That's what makes them a scalar. Now the last 2 there, speed and distance, we're going to talk about them a little bit more because we spent quite a bit of time in Physics 11 talking about how they relate to velocity and displacement. Okay, just scrolling up here a little bit. The second type of quantity that we're going to work with for Physics 12 are vectors. These are twice as cool. They not only have size, not only do they have magnitude, bigness, they've also got direction to them. Now that direction sometimes might be indicated with north, south, east, or west. Sometimes it could just be like positive for a forward velocity and negative for a backward velocity. So here are a few that we would have looked at in Physics 11. Force, you can talk about how many newtons it is. Okay, there's your magnitude, and then which way, up or backwards. Same with acceleration, it also has direction. And velocity and displacement, those are also vectors. They have some direction intrinsically attached to them. Now, the ties between speed and velocity and then distance and displacement, let's spend like 1 minute here talking about it and then not really worry about it again. Okay, it was kind of more of a Physics 11 issue. So speed is just how fast you're going. If your car is going forward at 4 meters per second, positive 4 for its velocity, you would just say, yeah, the speed's 4. And if the car is going backwards at 4 meters per second, like negative 4 meters per second, we would say, yeah, the speed's 4 meters per second. So that relationship is actually pretty easy. All we do there is essentially absolute value in terms of math. The relationship between distance and displacement, it's a little more subtle. You actually need some good calculus to get it totally dialed in. You can say, well, it's the same. If my car displaces positive 4 meters, the distance is 4. Yeah, I'd agree. And if my car displaces negative 4 meters, my distance is 4. Yeah, I agree with that too. But what if your car starts in one spot, goes forward 4 meters, and then back 4 meters? That displacement is 0, but the distance is 8. And you can't take, the absolute value of 0 and get 8. So the relationship there is a little bit more subtle. And you know what? That's about all I want to worry about in terms of the difference between speed and velocity and distance and displacement. For our work in Physics 12, the letter D in our formula sheet is going to be displacement. We do need to talk about how to describe the direction of a vector. So if you could just draw a little compass rose there, north, east, south, and west, and then stick a vector on there. It's a displacement vector of 3 meters. It's not quite northwest. So if somebody says to you, northwest, well, that'll be right down the middle, 45 degrees up from west. This one's just a little closer to west. Okay, I want to talk about how you could describe that vector. Let's say you grab a protractor and you notice that compared to the east-west line, it's 42 degrees. Now, little foreshadowing, whenever you can, always try to measure angles compared to that east-west line. It's just really nice for the math. So this one's 42 degrees up from west. So how are we going to describe that? Well, in Physics 11, we said that one way to do it would be to say, yeah, it's 3 meters. And then the direction, historically, physicists love putting directions inside square brackets. So here's the direction, and it says 42 degrees on the north side of the west line. So west is your baseline, and then we've twisted by 42 degrees towards the north in order to describe that direction. You could have come from north and headed west. That would have been 48 degrees. So the same direction could also have been called 48 degrees west of north. But I'm going to suggest to you it's actually nicer if you don't do that. It's accurate, but it's just nicer if you don't. The little arrowhead on top of the D here is completely optional. You can put it on there and say, hey, look, it's a vector, right? Just to sort of emphasize that. Now, that's not the only way to talk about that direction. Mathematicians love to talk about directions measuring from their x-axis, east if you wish, and they go counterclockwise. Now, there's a good reason for them to go counterclockwise, but as they do that, it looks like, well, 180 minus 42, 138 degrees. So mathematicians might say, you know what? I'm just going to tell you that that direction is 138 degrees. No north of west, south of east, none of that stuff, just a number, 138 degrees. And our textbook does that occasionally. It's actually a pretty common thing to do in math, right? Because math people and physicists kind of all interrelated. And 138 degrees could be a way to talk about that. You should know, though, that some people, like pilots, they like to measure from north, clockwise. So they would say, okay, 90 to get to east, 90 to get to south, 90 to get to west, there's 270, and then 42 more. A pilot would tell you that that direction is 312 degrees. Nothing wrong with that, as long as you know who you're talking to. Are you talking to a pilot? Are you talking to a mathematician? What if you're talking to a pilot who likes math? It gets complicated. So it can be done as long as you know who your audience is. Now, lots of times in Physics 12, we're going to do questions and people are going to say, oh, can you get the answer, but just give me magnitude only. And it sounds scary, right? When they're like, ooh, magnitude only, like it's some sort of dangerous instruction. But that just means relax. Only give me half the answer. Just tell me how big it is, right? And here it would be 3 meters. And actually, technically, you wouldn't put the arrowhead on the top of that D. You would say, okay, it's not a full vector right now. It's just the size part, right? 3 meters only. Okay, so we're going to play around a lot with vectors, things that not only have magnitude but also direction. And we're going to spend the rest of this lesson just looking at adding vectors. We're not even going to get it all done. We'll still need the next lesson to look at the third method. So I want to show you 3 different ways that you can add vectors together by the time this is done. First method is the graphical method. We actually didn't do this in Physics 11. Something close to it, but not exactly this. So here's the plan. You need to use a scale diagram. That's what separates this from our work in Physics 11. We never did that. But then when you're ready with your scale diagram, we will connect the vectors up head to tail. That sounds familiar. We did do that in Physics 11. So here are 2 vectors that we're going to go and add together. Hey, I apologize. I probably should have put arrowheads on top of these vectors just to really denote that they're vectors. I didn't get to that. Why is it a V? I don't know. V for vector, V for velocity, whatever. Doesn't really matter. They are velocities, though. 20 meters per second. And then the direction looks like northeast, 45 degrees north of east. And then a larger one, 25 meters per second. Not northwest, though, right? 30 degrees up only. And we're going to try to see if we can find this sum, vector 1 plus vector 2. Okay, that's our goal for the rest of this lesson. We're going to do it 2 different ways. Maybe move down your page about like 1 hand width, maybe, I don't know, about 8 or 10 centimeters, and then draw yourself a little compass rose, a little plus sign down there. That's where we're going to begin. And here's how the game works. You have to draw a scale diagram as best you can. So I would start by taking a protractor and, well, sorry, I got to back up. We need to pick a scale for our scale diagram. I propose this one. 1 centimeter on paper could represent 5 meters per second in the story. I just noticed that the 20 and the 25 are both divisible by 5, so I think this will work well. Now my plus sign down here, here's what you'd have to do. You'd have to drop your protractor down and measure up very carefully 45 degrees up from east, and maybe just put a little mark on your paper right there, just 45 degrees up. And then you can take the protractor away and then take a ruler and measure along that 45 degree line exactly, in this case, 4 centimeters, right? If they're 5 meters per second each, 4 centimeters, yeah, that gets you your 20 meters per second. So you want to carefully measure the length and then draw that vector in. Do yourself a big favor, stick an arrowhead on the end. That's the first vector. Good idea to draw another little compass rose up at the end of that, and then we're going to play the game again. Now the next vector doubles back to the west, okay? It goes back left. So you take your protractor, carefully level it right on that end of that first vector, and we'll measure up from west, up from that left side by 30 degrees. Maybe put a little hack mark there. Take your protractor away, take your ruler. Hey, if we want 25 meters per second, 5 meters per second for each centimeter, we need 5 centimeters. So then you very, very carefully draw a vector, an arrow that is 5 centimeters long and pointing at that 30-degree angle. And stick an arrowhead on the end. Okay, mostly done. Now, do yourself, again, another huge favor. This is for yourself, not for me. Switch colors. Grab a different color pen. Make this next vector look different, because this next vector is the answer. Well, you think it'd be called the answer, or maybe the result. But the mathematician said, no, when you're adding up vectors, instead of calling it the answer or the result, we'll call it the resultant vector. So there's the answer, and it goes from the beginning of the first vector all the way to the end of the last one. So the arrowhead is up there at the top left. If you switch colors, it's kind of like that Sesame Street thing, one of these things is not like the other, right? One of these things does not belong. You can look at it and go, oh, that green one's special. Yeah, it's the answer, right? What we need to do now is figure out which way does it go and how long is it. Remember, every centimeter is worth 5 meters per second. So you then take a ruler and you go, okay, it's, this many centimeters long, I don't know, 5.7, whatever that is, right? And you say, okay, 5.7 times 5, and then you can figure out how many meters per second that's worth. And you grab a protractor and you do your very, very best to measure the angle as well. And if you do that, you can then say, okay, here's my answer. And I just put a little R subscript down here just for resultant. So my vector resultant, my velocity resultant is 28 meters per second. That was my length multiplied by 5 because of my scale, right, because of this. And 74 degrees north of west. So that's the graphical method. It's completely visual. Right? It's really, really nice that way. You might think, oh, it's slow. Actually, it's not. It's actually pretty fast compared to the next method we're going to do today. But it lacks precision. If you were to do the exact same question again, you might get 27 meters per second, maybe 75 degrees north of west. So it lacks the ability to dial in many sig figs over and over to the same value. So let's see if we can find something that is more precise. But I'll warn you, it's longer. So, next option. Let's talk about breaking vectors down into their components, into their parts. And to do that, the verb there is to resolve the vector. It's kind of a nice little math rule out there that says any vector problem can be broken down into two vectors as long as they're perpendicular. And that's what that crazy upside down T means. So that's what we're going to do. We're going to take each of those two vectors and we're going to break them up into some perpendicular ones. It's going to take a little time. So my first vector was 20 meters per second, 45 degrees north of east. All right. Just going to draw a little quick sketch of that. I don't need a protractor, don't need a ruler, just a quick little sketch. But definitely use a couple of colors. The blue is the vector, and then the green ones are those resolution vectors to break it up. So vector number 1 has an x component, a sideways component, and it has a vertical component, a y component. And now you play your right angle trigonometry game, your SOHCAHTOA, so to speak. And you might say, oh, okay, well, cosine. Cosine would be adjacent, v1x, divided by hypotenuse. And that's great. There's part of SOHCAHTOA. But you need this, right? We know cosine of 45, and we know v1. It's 20. We're trying to find v1x. So you have to multiply both sides by v1. Hey, we can get there. It's going to look like that. So 20 times the cosine of 45 gives you this irrational number, 14.142. Now, we're only getting started. So I'm going to write down 5 sig figs, and then I know I'll have 3 good ones in the end. So vector number 1 goes east by 14.142. Okay, keep going. If you did sine, thinking of SOHCAHTOA, sine would be opposite divided by the hypotenuse. And again, I want the opposite. I want that v1y. Multiply both sides by the v1, by the 20, and we're there. Now, the observant amongst us would say, hey, 45 degrees northeast, we knew they were going to be the same number. They're both 14s. Yeah, that's true. But generally, that wouldn't be true. So just kind of going through the motions here. I guess you could have done Pythagoras, if you wanted to find that v1y, if you already knew v1x. So there, we've successfully broken down vector number 1. Now we have to do it for vector 2. But let's be smart about this, because we're going to be doing this hundreds of times. Don't get bothered by that, but it will be hundreds of times. Every time you're going to start off with, your SOHCAHTOA mathematically, and you're going to be multiplying by the hypotenuse. Every time it's going to look like this. The hypotenuse gets multiplied by a cosine in order to find the x part. And the hypotenuse will get multiplied by sine in order to find the y part, as long as you promise to have your angle down here compared to that east-west line. And that's why I strongly encourage you to draw it there. So I'm going to use that idea to do this next one fast. So vector 2, 25 meters per second, 30 degrees north of west. Okay, little sketch. It doubles back left. I want to find these parts. Sometimes they're called the projections. It's kind of like that blue thing is some stick stuck in the ground, and if you had the sun overhead, it projects a shadow down onto the ground. That would be V2x. Or if you had like a car over on the right with its headlights shining on that blue stick stuck in the ground, the V2y would be like a shadow on a wall, right? So we're trying to find those projections, those shadows. Let's do it fast. Don't slow down. You don't have to think about SOHCAHTOA. You want the x part? Use cosine. 25 cos 30. Done. It's an irrational number. It's around 21.6. And it goes west. Then the vertical part. Don't even have to think about it. You don't have to think about SOHCAHTOA. You can go vertical, it's y. It's going to be sine. 25 times the sine of 30. Actually, that's a really nice number, the sine of 30. It's not irrational. It's exactly a half. So we get 12.5 on the nose, and that's going north. Okay, so we don't have to think about it at all. We can just use cosine for x, sine for y. It's even alphabetical, right? Like cos comes before sine alphabetically, and x comes before y alphabetically. So nice, easy way to remember it. Now we have to put those four numbers together. Okay, just looking back here for a second, I've got to put this 14 east, this 14 north, together with 21 west and 12 north. And we're going to do it just component by component. We're going to take our time. So we're going to add the components up. We're just about done. Okay, let's go x direction first. Let's take just the x part of number 1 and just the x part of number 2, and we'll find out what the x part of the resultant is. Now, as you remember, this particular pair of vectors, one was going to the right, to the east. The other was going left, to the west. An easy way to figure that out mathematically, to dial that in mathematically, to model it, is to just use negative numbers. So we can say, hey, to the right it's positive, 14, and vector 2 was back to the left by 21. So the negatives win here. We've got more west than we have east, and that's what that negative 7.5 is talking about. Same thing with the y's. But here in the y's, they actually cooperate. They don't fight. So you've got a 14 north working with a 12.5 north. This resultant vector really goes north by a lot, 26. Now what we have to do is patch those two back together. And I should say that some people would say, why bother? You're done. You've got two numbers to describe this two-dimensional answer. That's true. You know, a little bit rich on the sig figs there, but we could stop with just those two numbers and say, yeah, there's my answer, giving you the x and the y. But they gave us vectors that had a diagonal length and an angle. So it's good form to return the answer in the same way. We'll give them a diagonal length and then an angle. Now, remember back here when I was saying, hey, if you put the angle compared to the horizon, it's so nice because cosine is x and sine is y every single time. So in order to create this picture that has an angle naturally being formed compared to that east-west line, when we draw the answer, let's go x first and then y. It's not wrong to go the other way. It's just that if you do it this way, 7.5 first, stick an arrowhead on it, and then go up 26.6, the angle that you create in that little right angle triangle naturally forms on the east-west line. Really nice to do that. Now, how easy is this? A little Pythagorean theorem, okay, little Pythagoras as we like to just quickly say, and we can figure out that this thing is 27.7 long. I've got two answers here because in Physics 12, this is just a reminder for me to remind you, just like in Physics 11, don't mind if you go 3 sig figs or 2 sig figs, regardless of what you see in the question. I know that's not technically right, but regardless of what you see in the question, as long as you go 3 or 2 sig figs, we're good. So either of those would be great. And then I would take this opposite and adjacent, the 26 and the 7. If we divide those, we can do tangent in reverse, right? So tan of the angle, the TOA part of SOHCAHTOA, would be 26 over 7. So find that value of 26 over 7 and then untan it, right? You want to go backwards. So that's inverse tan. Actually, it's technically called arctan, but yeah, we like to say inverse tan. It's the second function on your calculator, but yeah, inverse tan. I jokingly call it untan. Right? So we're going to untan that, and it's 74.3 degrees. And we're done. Not only this question, but pretty much this lesson. The resulting vector is 27.7 meters per second, 74.3 degrees north of west. What's neat about this is precise. In other words, if you did this again and again and again, you're always going to get those numbers. The graphical method lacks that. But it's not incredibly visual. The graphical method is way more visual. It'd be nice if there was something that combined everything, like speed, nice visual picture, and precision. And there is. And we're going to do that in the next lesson. But I should tell you that we'll still have to use this method, or we generally will use this method, if there are a lot of vectors to add together all at once. So final little note for the day here. If you've got like 3 or 4 or 5 or 7 vectors to add together, this might be the best way to go. Think about what their components are, and then go from there. And so that's going to wrap up the first lesson. We've got 2 out of the 3 methods for adding vectors together done. And in the next lesson, we're going to look at the third, which kind of is the best of everything. And then we'll look at subtracting vectors. But this first lesson is totally taken care of.